Alright, so a quick video lecture on polarity and polar molecules. First off, polarity has to do with the electronegativity of the atoms. And if we're going to talk about something being polar, very similar when we talk about magnets. Magnets has two polar regions, a negative end and a positive end. And just like in magnets, we can, if we put a opposite charge near, they're going to attract. If we put a similar charge near, they're going to want to repel. So this polar molecules are going to follow the same basic principle. Polarities, to determine if a molecule is polar or not, we're going to look at an electronegativity difference of 0 to 0.7, saying that it's nonpolar. And if the electronegativity difference is above 0.7, we're going to call it polar. Now, the only time that this is going to not stand true is if the molecule is symmetrical. If it's symmetrical, it's always going to be nonpolar. If it's asymmetrical, it can stay polar. So let's take a look at some examples. If we have hydrogen bonded to chlorine, now hydrogen has an electronegativity of 2.1, and chlorine has an electronegativity of 3.0. So we have an electronegativity difference of 0.9 in this direction. That means that HCl is going to be a polar molecule. So what that means is when we have hydrogen and we have chlorine, this shared electron pair that's bonding our hydrogen atom to our chlorine atom will spend more time around the chlorine atom, meaning that the chlorine atom will have a slight negative charge. The hydrogen side will have a slight positive side. Now notice, this molecule is non-symmetrical. If we were to take hydrogen, HCl, and fold it in half this and compare it this way, hydrogen is not the same as chlorine. They're not symmetrical. So HCl can be a polar molecule. If we take something like hydrogen, well, hydrogen is a diatomic element. Hydrogen's a diatomic element. We have an electronegativity of 2.1 and electronegativity of 2.1. So there's no difference. This is non-polar. If we take a look at, let's say, CH4, well, carbon has an electronegativity of 2.5. Hydrogen has an electronegativity of 2.1. So each one of these bonds is only an electronegativity difference of 0.4. 0.4 is less than 0.7, so it's non-polar. The other thing to think about is that this tetrahedral molecule is going to be symmetrical. So that also leads us to believe that it to be nonpolar. So let's take a look at something else let's take a look at another polar molecule, water, H2O. Water, actually a bent molecule, so let's go ahead and take a look. Oxygen has an electronegativity of 3.5. Hydrogen has an electronegativity of 2.1. So that means each one of these bonds has a difference of 1.4 towards the oxygen end. So this molecule is going to be polar. While water is symmetrical this way, it is not symmetrical this way. So our oxygen atom will receive a slight negative charge, and our two hydrogen atoms will receive a slight positive charge. So if this oxygen, or if this water molecule comes near another water molecule, these charges are going to attract, and there will be a bond that forms between the oppositely charged parts of a polar molecule. This is called a polar bond. So this is part of the reason why when we look at water, water will bead over and not fall, because there's a whole bunch of polar bonds holding those water molecules together. Let's take a look at carbon dioxide. Carbon dioxide is CO2. Now here, carbon has an electronegativity difference of 2.5. Oxygen is 3.5 and 3.5. So there's a difference of 1.0 and 1.0. This should lead us to think that that carbon dioxide is polar. However, you have to think back to physics. Okay, think back to physics. If a force is a push or a pull, right? So if we have one force pulling this direction with a force of 1.0 newtons and another force pulling back this way at 1.0 newtons, the resultant force is 0. Same thing that's going to happen in our carbon dioxide molecule. We're getting each oxygen atom is going to pull on those electrons, but that pull is equal and opposite. So this is going to be a nonpolar molecule. If you look, carbon dioxide will be symmetrical this way and this way. So this is a nonpolar symmetrical molecule, even though the electronegativity difference is greater than 1. When you get into biology next year, you're going to be talking about the cell membrane, which is called a phospholipid, bilayer. Now, these phospholipids are very large covalent compounds. And sometimes when we have these large compounds, we can get two distinct areas. We can have a polar region and a nonpolar region. So notice the two nonpolar regions tend to come together, and the two polar regions are facing away from each other. Now, when we're talking about this phospholipid, we're talking, if we just take one of those two tails, we're looking at a tail that'll look something like this, with each one of those bonds being bonded to each to a hydrogen atom. So this is a very large molecule. So very large molecules can have regions of polar and regions of nonpolar areas. So again, just taking a look, from 0.0 to 0.7, we're going to call that nonpolar. Above 0.7 is going to be polar. And then we also have to take into consideration symmetry. If it's symmetrical, it's nonpolar, even if the electronegativity difference is greater than 0.7, because remember, equal and opposite poles. If there are Electronegativity poles, if it's symmetrical and they're equal and opposite, they're going to cancel out. If they cancel out, it's going to be nonpolar. Asymmetrical will tend to be polar. Good luck!